good.
Yeah. So let's start. Can I start? Can I start?
Start? 10 minutes already?
Yeah, I'm not sure.
So fast.
Yeah, I'm not sure that exact. Maybe 40 or something. I'm not sure.
Oh, maybe not yet. Okay, 40.
Yeah, you can decide.
Okay, they make
Yeah, 40.
40.
Okay. So actually, today is all the training of by using a supercomputer. We have provided 5 kind of sample programs. So it's a free time to use it.
Okay, that's good.
So
that's
not
good.
so crowded. This is only final slide of the.
For the lectures today. Okay, yeah. I think, yeah, your design very
Yeah,
good.
because I have a question with what is MPI. so I just explain this slide. So that's a yeah. That sample program is the only sample program. So
see.
the
So they
attender
just-
cannot understand how to the
Okay.
MPI. But
So you will
yes,
talk about-
yeah.
That's nice.
Yeah. But basically, the slide is based on the something computer science, but
Yeah.
not so. I think the complexity
Yeah, it's
content inside, so it's okay because I have a same lecture for University of Tokyo to teaching MPI to the other something civil engineering or something by using the same text. Yeah.
So you have this kind of course like every year,
every
semester.
every semester. So that means 2 lecture, 2 times per year.
Okay.
Because a semester has a half what you say half year.
Half
Year is
yeah.
one lecture and half year is one year.
I see.
So
Okay.
the summer season and the winter season.
Winter season. Oh,
For 8 years. That means the 60 classes.
you have. So you wrote your book.
Yeah.
Based on-
But it's Japanese. So
You should.
so they exactly same. So book has published, but it's Japanese. So no use for that.
We should translate that.
Yeah. There is a project to publish English version with the other community with maybe a physical thing. Because I have a lecture for this one, so to the physical scientist in Japan. So
I see. So
maybe you
put
can
some-
see.
That's very good.
Yeah.
If it is English, then we can.
This is the first time to translate the English material. So maybe nice
Yeah.
things.
In
We
the
can,
future.
yeah, and I can use this one.
You see, we call this one.
Ah,
we
yeah,
put
yeah,
on
yeah.
YouTube,
Yeah,
and
it's
then
okay.
Your book can have a link
Yeah,
to this.
yeah, hopefully so.
It's very
Anyway,
nice.
yeah. Actually, there is many English materials for MPI, but
Yes.
kind of very difficult because
I see.
it's based on the computer science based, so they're very grammatical and some I think not so useful. For,
Yeah, because I think many people are sort of computational science,
yeah,
physics,
yeah.
mathematics.
Yeah.
They need to know these things, but maybe more basic.
That's exactly same situation in Japan. So that's why I made some material which maybe can go make some FDM fluid dynamics based on something like. Yeah. Anyway.
Maybe. Oh, maybe. But we have time. We can discuss something about our project.
Yeah.
So right now we are writing a paper about the randomized
Yes. Algorithm.
integration
Yes,
of
nice.
SVD.
Yeah.
I have 2 students. They are working on that. So I think they. I asked them to attend this course
I see.
to think about how to do that
Okay.
in maybe this parallel computer. So later I think I will just send you the C version of the code and some reference. And after we finish out writing our paper, I will send you a copy.
Nice.
So I think you can. The paper is sort of many mathematics, but probably you can skip that. The algorithm itself is actually
parallel algorithm.
It's not too complicated. There's some mathematics derivation is complicated, but maybe you can skip that. And then we can try to run some big problem.
Actually, you can use the FX10 through this project, and you can use. I moved to Nagoya, so also same style. So maybe it's really convenient for your student is okay. Your students, I think they can use.
Okay.
Especially in University of Tokyo, because there is a MOU.
MOU.
But in our case, I'm not sure, but I will check. But maybe we need some amount of MOU. But there is only many possibility to use it. Anyway, so 1 minute. Okay. This. Is that okay? Okay. Okay, so it's time to start part of the lecture. So I'd like to explain the overview of the MPI. So I have some question for what is MPI. So it's right. So I explain the MPI basics in this slide. So there is a danger. So I explain the features of MPI first, and I pick up some basic function of the MPI in this lecture. And these are some example of the dense matrix operation, like dense vector multiplication or dense matrix vector multiplication. So features of MPI. So the MPI is not library. So MPI is a specification for a message passing library. So the MPI specifies how to communicate the messages with distributed memory parallel machine. So by using the MPI, so we can extend the parallel program to very large scale computations. So that means that we can dramatically reduce the execution time by using the MPI, and we can use a very large memory. So with respect to the aggregated memory size of the total supercomputer system. And the important thing in here is that portability, because all supercomputer company supported an MPI. That means that if you write MPI code, you can execute your MPI code to every supercomputing environment. So that's a very nice situation. So when I was a graduate student, there are many communication libraries. So it depend on the computer vendors. So it's very terrible situation. But in now, standardization is established by using the MPI. So it's easy to do execution for the many supercomputers. And basically MPI, so if you have implemented the highly parallelism by using MPI, so it can establish high performance. That means the scalability is nice. But some people say that programming is very hard because the communication is explicitly written, so the kind of tough. So, but if you understanding how to implement the MPI, I think not so hard. So there are many trainings things, and including this lecture and Professor Kengo's one, so you can think that not so hard by using the MPI. So this shows the history of MPI. So the MPI specification is specified by the MPI forum shown here, and the first version is named MPI1. It is established in 1995. So that's a kind of young language or some specification compared to the other specification like Fortran or some parallelization language. So currently, so we maybe so MPI MPI forum try to specify the version 4, but so by using the MPI, so MPI 1 is recommended. It's a very basic one. And so the Argonne National Laboratory have developed for the reference information, reference implementation. So, and in that phase, so many persons using this reference information, reference implementation, and MPI will be common in that phase. So in version 2, so I don't mention this version 2, but so the extension is done with parallel I/O, something C++ and Fortran 19 interface, and so runtime creation and killing specification. That is to establish the master-slave parallelism like this. So in the version 3.0, so currently some supercomputer supports MPI version 3.0. So the one of important features of version 3.0 is providing a non-blocking reduction operation. I will explain this later. So usually the communication is done with a blocking way. Blocking way means that sending is issued and the other receiving is issued. So that's kind of there is synchronization. But by using this I means non-blocking case, so we can remove the synchronization. And in this case is that MPI all reduce. So maybe you know the reduction operation in the OpenMP. So same interface is all reduced in there. So by using the I interface, so the synchronization is not. This version is a non-blocking version. So that means that the synchronization free version. So in version 3, they provide a new function in there. So this is a remarkable function. Well, other things are one-sided communication. I will skip on, but so they are more sophisticated function thinking and specified by version 3.0. So current version is 4.0, but I'm not so familiar. But one thing is need to mention is that to consider the fault tolerance, because so that in current MPI, one of drawback of MPI is that no fault tolerance, because one of MPI process is down, all of MPI process is down. So that is a very severe problem. But to remove this failure, so that we need to think about the fault tolerance. So the version 4, so they try to specify something like fault tolerance, but I'm not sure the final result. So if you have interest, please check the specification through this page. So back to the MPI implementation. So MPI is not so MPI library, so that's a specification. That means that there are many implementations. So one of famous implementations is the MPI-CH. So we call it MPH, this version. So this is developed by the Argonne National Laboratory, and this is free software. You can install the MPI by using the MPI-CH in your environment. So very famous. So another, of course, there is another MPI implementation. So OpenMPI is another one, and LM, this is a very classical one, but so there is many implementations. This is a research version of the so our center dean, Professor Ichikawa, but so there are many implementations. So you are using the Fujitsu's implementation of MPI. So in this case, very optimized for the supercomputers. So first choice to use the MPI is that, of course, the vendor's MPI. And you can use, what they say is that you can use directly through the vendor's MPI in your supercomputer environment. So the thing is that how to write the communication by using MPI. So analogy of the communication is almost same as the postal sending. So that you can imagine that if you send a mail, so you need to specify the sender's address and addressee address and location of the contents. So this is obvious because inside the envelope, but know it. And so there is a classification of the content, something like a paper or a book or something like that. And so the amount of contents, that means what to say, the weight of the inside ingredient or something. And tag, so maybe you know tag to send the maybe box, so many boxes sent to the same place, so the to specify the content, so we make the tag. So there's a tag information in there. So in MPI, all same things. So the address is directed to the ID. So MPI words, that means a rank. And of course, the receiver's ID needed. And so the address of the sending data is a kind of array address. So directly specify the array address. And the type data is that that is type of the array, something like an integer, real, or something. So amount of data is a number of the arrays. So specify that one, and also MPI need to specify the tag number. So so MPI, so we have more than 300 functions. So it's really tough to explain all, but I pick up very few functions, and you can understand these okay to write the code for MPI. So first one is the system function. So the MPI init, the MPI com rank on this one is a very system function. So initialization and the finalization to get the identification number. And another one is basic communication, one-to-one communication. So this is sending and receiving. And there is two types. One is the blocking type. That means that synchronous communication, almost synchronous communication. Different will be explained later. Or the next day I will talk about non-blocking one. But you need to know the blocking type in first. So MPI send is a sending function. MPI receive is a receiving function. So another thing is that broadcasting function. So that means that same message to send to all processes. Only one specification. So this is MPI bcast. So another one is the reduction operation. So the MPI reduce, MPI all reduce or something is provided. And so there is a time measurement function. So the name is MPI right. So I think that it's okay to know like this. So I think it's not so hard to run about it. So I'd like to mention the one very famous common variable from the MPI. So that is the MPI conword. So this is called the communicator. So communicator basically defines the processor group to perform an operation. So so initial state. So the ID can be named from the 0 to the maximum number -1 for the connected to this communicator. So the common name, so the reserved name is the MPI conword. So that's why the whole MPI program is written by this. So because this is a reserved variable. So this is a kind of advanced usage, but you may use this. So I will mention this. So if you want to divide the processor groups, so you need to use the MPI split command to MPI conword processes. So that means that if we use 9 processes, and somehow we needed to regroupment of the three processes. So by using the same communicator, so by using the comma split, we can separate the process group. So in this group, separation, for example, so same different message is sent within the different groups, only one operation. In that case, you use the MPI comma split by splitting the MPI comma word. But this is the advanced one, so that if you need to use this kind of process, please remind of this function. So back to the basic MPI function. So we basically MPI traits the processes. So the formal description is MPI processes, but it's very long word. So especially I use PE. PE means the process element. Directory means the MPI process in this lecture. And the name of the identification number in MPI is the rank is specified. Rank is the ID number for MPI. So MPI program is so we mentioned, so only one program is in there. So if we use the whole MPI process, so same MPI is copied. So if you use the 10,000 execution, also 10,000 copies are made in this way. And rank is named to something like this way. So rank 0 is somehow process, rank 1. So unique number is allocated to rank number. So actually, so there is two interfaces. So one interface is for MPI is written in C, and another one is Fortran. And natively, so the MPI is determined the C interfaces. But you can use the Fortran interfaces. So some relationship is that so for C, so you know that there is a return value. So the return value is error code. So this style is a very common style. So IERR equal MPI something is the common style. So if you are Fortran user, so please error is the last part is an error code and call the target procedure like this. So almost same. So another difference is that system array for MPI status type. So you can write you can see the difference allocation, but this is a small modification. So basically, so I'll explain the MPI specification by using the C interface. Fortran user can reconstruct the usage, something like that. So the other difference between C and Fortran language is that its type. So the chara is a character in C language, and Fortran is a character, and main differences maybe float is a real one, and C is double is a real double, but Fortran is a MPI double precision. But this is the same as the original type definition of the each languages, so I think no problem to use. So point in here is that to specify the type, so you need to use MPI underbar for original type definition. So for the first interface, so I'll show you some MPI receive function. So MPI receive, you need to write this one. So first one is a receive buffer. So usually this is the first address of the arrays. And the second is the count is integer type and specifies the number of elements of the received area. And the type is I mentioned, so that if you use float type, the MPI float should we write this letter to this part. And isource is so sending P rank should we write in here. So if you arbitrary PE is accept specify the MPI any source directly in here. And the tag is a tag number for receiving data. And if you don't mind the tag number, so special MPI any tag. And the communicator, so usually I mentioned, so that you can specify the MPI com word directly in here. And one thing don't forget this one is that you specify I status by allocating the I status type by your own and specify this part. If you forget, it makes a very dangerous parallel programming because so it depends on the compiler. Some compiler accept and work the parallel, but some compiler cannot work. So if you omit this one, so basically it can work, but some situation can work. So that means that the debug will be very hard, and this is illegal of the syntax. So the point in here is that the receive need to allocate the I status arrays by using the I status type of the C. Fortran language case, so C case is only write this MPI status I status is okay. So Fortran user needs the integer status MPI status. It's an array of the integer type is needed in advance allocated. So don't forget that. So this is a receive function, but so the correspondence handling is shown here. So this is a kind of almost same, except for the I status situation. I will omit this explanation. So, but it's okay. So in this situation, we do something like this communication. So rank 1 call the MPI send, and rank 3 call the MPI receive. So this communication is established. So the other process, like 0 and 2, I don't know, and not committed to this communication. Okay, so we can write send and receive something like communication, this communication. Okay, so the next one is that broadcasting function. So this is one message sent to all processes by using the one interface. So firstly, so we need to specify the address for sending and receiving area. Kind of interesting things, because some process sending array in here, but other processes receiving the same array in here. So that means the sending and receiving area is specified in here. So this is because MPI program is only one. Okay, so the other things, the count is number of elements, and data type is data type. And the point in here is that you need iRoot information that specifying the hold the sending message. If specify 0, so rank 0 send the data. So this is this by specifying this information to know sending or receiving. So this is a really interesting point for this interface. So anyway, so we can write only one line to the sending data by using the MPI. So in this situation, the iRoot is set to 1. So this is the sender. The other is the receiver. And the important point here is that all processes should be called the MPI biggest. If you don't call this but the process is stopped in here. So that's the point. So I mentioned the FT. But all process is called the MPI bcast. Bcast is started. So this is the message. So the all same message is sending with one line. So this is the behavior of the MPI bcast. So I'd like to reduction operation of MPI. So what are reduction operation? So what are reduction operation? So reduction is something degradation of the dimension. So something like the dot product reduce the dimension vector to a scalar. So something like that. In the parallel processing, also providing some processes. So another word for the parallel processing, the collective communication. That means that collective operation for the many processes. So we call this one two. So in MPI, there are the two interfaces to do reduction operation. So here is an example. So first one is MPI reduce. So MPI reduce executes some reduction is doing with several multiple processing, and result should be stored one rank. In this case, 0. So you can specialize 2, 1 is okay, but result is only setting one process. So another one is all. So all means all process have a result. So in this case, it's 3, 0, 1, 2 processes has a operated result. So there are the two different ways to do a reduction operation in MPI. So I would like to show you some this MPI reduce interface. So MPI reduce, firstly, is you need to specify the sending buffer. So the sending array in here. And secondly, the receiving array of address. And the point here is that the area of sending and receiving must be different one. So this is the kind of implementation matter inside the MPI, but you need to different ones. So say you allocate some A for arrays, so you need to allocate the B or something, or you need different address in here and here. And the count is that is a count of a specified array, and data type is a data type. And there is some interesting data type. So MPI2 integer or MPI2 real is I'll show you later in this data type. Operators. So there are many operators, but we frequently use one is MPI sum or MPI max or mean. That means that it directly shows this one. Sum is a summation between the processes, and the max means get the maximum value for all processes. Mean the minimum value, something like that. So I root is that rank number to store the result shown specified in here, and communicator is specified here. So that's all for the reduction. So we are doing now. So the same as MPI bcast, all process need to call the MPI reduce, and we set to the process 1 in iRoot. So data is something operated and summation, so get the final data. Only this processes. So this is the behavior of the MPI reduce. So this shows the MPI 2 doubles precision case. So this is a kind of interesting interface. So we have two listing here. So in this case, two double precision data, and root is specified in here. So in this case, so we specify MPI max log. So the answer is, in this case, is here 5990. Or this is compare the first column and the maximum one is 5.9, so the get this information to something like the database accessory, but we can use this kind of a process for some numerical computation. So one of them is the pivot selection of LUT computation can be implemented in this interface. So another thing is the MPI all reduce one. So this case is almost same as reduce. But difference is that there is no iRoot. So in this case is that operation is done. So after that, so the broadcasted operated result and get the same data all processes. That's our behavior. Of course, with respect to the performance, so the MPI all reduce is slower than MPI reduce because there is MPI bcast inside. So that's why. So from here, so it is better to use the MPI reduce if you are okay. So because there is extra broadcasting in there, in viewpoint of performance. So another things maybe so the dense matrix computation. So we may gather the data. That means the matrix data to one data. So in this case is transposed matrices. So in this case is ABC is the distributed data. So to do the transpose, so we need to gather ABC part in here. So in this case, we use the MPI gather interface or MPI. And MPI scatter is also opposite way, but we can implement it transpose matrix by using the MPI scatter. Problem here is that so same data need to be gathered or maybe it can be scattered in this interface. If you needed to gather or scatter so different size of the message, so you need to use MPI gather V or MPI scatter V. So if you need, so please refer to this one. So I'd like to explain the one thing, the MPI gather one. So MPI gather need to write the size first part is that specify the first address to sending area. That means the address of the array. And second is its number of elements. And third one is the type and the receive buffer. But you think that there is something difficult to specify the count in this interface. So that means that in this case, so MPI, by using the MPI gather, if we gather the one size of data, 1, 1, 1, and gather to the 3, which size should we specify? That is a 1 or 3. The result is that the area sending receiving must be different. The answer is that so answer is that so you need to specify the per process size. That means that in this case is 1 is the result. If you specify the gathered size, in this case is 3, so the running when you running this MPI gather, you will get the error, runtime error of this interface. So that's the point to use the MPI gather. So in this case, so gather the data. So if we specify the processor 1 to the iRoot process, so that we can gather this is something like this. And the scatter is almost same, so I will skip it on. So the point here is that you need to specify the distributed size, same as the MPI gather. So in this case, it's so the process 1 is iRoot, so the data is distributed like this way. So if you want to gather the communication, so please use this interface. So I'd like to switch to the example of the MPI programming. So, so I'll skip on this one. So, but usually, so the supercomputer I showed you, but in you usual PC cluster, you need to write the MPI run, specify the number of MPI processing here, and execute the profiling here. But in your supercomputer, so we need the batch job scheduler, so the number of MPI process and the number of nodes should be write special description of the each supercomputer system. So program. So in this case, the executable file is copied with a 4 CPU, like this way. So execute simultaneously. So final topic is another topic is that how to allocate the MPI process to the other P means the core. So MPI process to the core, how to allocate. So basically, so it depends on the operating system because the operating system manages this allocation, MPI process to the target cores. So in the supercomputer system, so we can specify the allocated so theoretical size through an interface. So there is some interface in the FXN system, but so in this lecture we don't specify this one. So in that case, so if we omit the organization structure of the specification of the allocation, so the operation system does that. So why I explain this one is that the communication may be optimized because so if we communicate something a ring-way transformation, that the actual node is a very inefficient way to allocate this one, so the communication time is going up. So that's a bad thing. So the some user want to manage this allocation. So please take care if you want to know some details in there. So that's all of the overview of MPI. So is that some question? If no, I'd like to switch to the another part of the MPI supercomputer. Okay, back to how to use the FX10 materials. So we have another example of MPI. This is a hybrid MPI version. So if you want to hybrid MPI version, so please type this one. So CP make file underbar HY16 make file is a different comparing way to do hybrid MPI execution. Do make. So in this case, make clean and make. And in this case, almost it's same is generating the hello is at the target executable files. And then, so you also modify the lecture to lecture 6 by using Emacs or VR or something text editor. And submit the job PJ serve hello HY0 something. And you confirm the PJs by using the PJ start. So in this case, so you will see 12 times hello. So that is a very reduced printed compared to the 196. So why? So this is a different execution style. So before the explanation of this hybrid MPI, so we would like to show some this batch job file. So differences in here. So this is the same for the PI execution. So the difference is this one. So MPI process is set to 12. But you think that there is some problem because we have 192 cores, but only using the 12 MPI process. So there are another core is empty to do a job. So that's a problem. But there is a specification in here, so that is a OpenMP thread execution specified as 60. So that means that one MPI process execute 16 MPI processes. So total job number is at 16 times 12. That means 192. That means all cores are used for this style by using the MPI and OpenMP. So this is an example to do hybrid MPI programming. So this is a figure of the one node of the FX10 system. So the starting the MPI, so only one MPI is allocated to say core 0 in here. So we still empty for the another core, but so there is an invocation from the OpenMP by 60 thread. So all thread is used. So why using this style? So Professor Nakajima mentioned. So the communication between the memory is only doing the MPI. So by reducing the MPI, that means the communication time is reduced by using the all computing resources. That's why we are now investigating this style of parallel programming. So this example shows what it says, a sample of the hybrid MPI execution, but please note that the program is only hello world. There is no job for the OpenMP thread. So in this case, it's kind of fake. But you can use the this style to use your real program, and that means actual real programming. Okay. So back to the hello world program. So maybe you see that this program, and maybe you can understand the behavior of this one. But I explain how to learn this program. So you know that only one program in there in the MPI program. So when the MPI run is command is invocated, so the maybe in this situation 192 process, so copy. So this program are copied to 192 processes. So we are starting the first point, but you may think that very strange things in here because there are only integer allocation in here, but the process is 192. What's happening here? The answer is that we are only writing one memory allocation, but in the system allocated 192 different variables with only one line in this lecture situation. So my ID allocated 192 different variables in here, even in only one sentences. So something like that. So you can see the first line. So that is MPI init. That means the MPI initialization. So MPI start in this line. And the second line is MPI com rank. That means that is returns the rank number to my ID. So that's why the my ID is a variable name for the rank number. And third line is MPI com size returns the total number of processes to the numprocs. So of course, content inside value of numprocs is almost same from all processes, but my ID is different, because this is identification number. And then, so there is a print in here, so hello parallel world, so that's why we have 192 printed in here, and printed with my ID, that's a rank number, so that's why you get some different number in last part. And interestingly, you can find the randomly number in that. That means not sorted. That means that the execution is not so synchronized in part. So MPI program provides no synchronization. And please note that here. So the printed number, that means the rank, is not real execution. That means that that's printed from the I/O buffer. But so execution is different, I think. So maybe sequence is 1 for something. The execution, I don't know. So one is the process 1 is the first. What to say? So if you see 1, 4, 3, so this means that process 1 is first, process 4 is second, process 3 is first execution is not. Because this is buffer only printing. The real execution is I don't know. So please take care of this one to check the parallel program. So anyway, so you can find a random something like number. So that means that there's no synchronization in here. So final part is that MPI finalized. So this is the end of the MPI execution. So this is a very easy program, but this is a very fundamental program for MPI. Fortran is the same, so I will comment. I will omit the explanation. So in the sample program, there is another example to know what to say programming execution time for the part of the program. So in this measurement, so we use the MPI barrier. So that means that this is a barrier point to synchronize each process in here. And after that, so we call the time measurement function, MPI W time, and you can write every code in here. And you also synchronize the execution in here and call the MPI time function. So the wall clock time is that in this case T2 sub T1. So this is the wall clock time, and but T0 it is also allocated double for 192. That means that each process the wall clock time may be different because this is not hardware barrier, software barrier. That means that there may be delay for each execution of processes. So by using the MPI reduce, so we get the maximum wall clock time to T with rank 0, something like that. So this is one of measurement way to the any target programs. But please note that in user, so we don't use a barrier. That means that communication time is totally different each process is. That's the user. But in this case, is to understand very easily. So we put the desynchronization in here. Anyway, so you can use this sample program in sample program you installed. So we have 5 sample programs, and you execute hello. And CPy is the computational pi of parallel program, and you can also use this one. And the CPyM is that basically its same as a CPy program, but it includes some time measurement function in there. Another 2 is some example of the parallel implementation of the communication. So I will explain in here. Sorry, I will explain later. So one note of by using the Linux. So maybe you use some redirection. So it's that kind of input file in specified file in text file in here, and output file in specified in here. It cannot use in the MPI environment. Please note that you can use this in without MPI, but many supercomputer systems cannot use this kind of redirection in MPI execution because to optimize the communication. But if you want to specify the redirection, so there is a special format for the Fujitsu. So in this case, so you need to write MPI run minus mass standard in input file and minus mass O4 output is something. So that is exactly same over this writing. So this is a kind of frequently asked question for some supercomputer center. So because this is a kind of not so special case in many users, but you can, if you need to, you please define this one. Okay, so I'd like to use some parallel algorithm example. So that is including the wa, ich, wa, ni. So wa is a Japanese. So ha means summation. So there is two different summation example for by using the MPI. So basically, so you can write this one is by using the MPI reduce, but you can also write the process, inter-process addition by using the MPI send receive. So if we use the send receive, so we have some need to optimize the communication. So this example shows that example. So simple implementation, summation for the between the process data is something like way. So this is a sequential summation I called. So I'm not the rank 0, so receive the other data, and after that send the left process. Left process is something like that. So we let be my ID is my process. So the left process is that specified my ID -1, and the right process is specified my ID +1. So the getting the data from the left process and summation, and after that send the data to the right process is a very simple implementation to do process addition. So this is easy to understand to see that this figure. So we have 4 processes, and we have data, different data in here. So the process 0 firstly sends the data process 1, and the process 1 adds the 0, adds the 1 equal 1. So 1 sent to the process 2, something like that. So the point here is how to write this code by using the MPI. So we can easily implement this summation by using the MPI. So this is the code. Maybe you can find this code by only watching the this example. So let's see. So first part. So of course this program copied to 192 in this lecture environment. So first line shows that data. So data. In this case, my ID is inputted, but everything is okay. And DLS backer is that temporal summation result. And the third one is that if sentences, if my ID equal not equal 0, that means 0 process 0 is pass this if sentence is. And the other all processes enter the if sentences and call the MPI reduce receive function. So the other all MPI